Okay, today we will start, as I told you also last time, with sliding mode control. And if you remember last time, this part is correctly recorded. I showed, in general, I showed the unrobustness of some possible approaches. But in particular, even though controlling the system using an integral, we have some robustnesses. But nevertheless, you remember the last example was assuming that I want to track a sinus function. This particular case, for instance, even though we have the presence of the of the integral, we are not able to remember to reduce to zero asymptotically the error between what I want to attain and what I have. And of course, it could happen, depends, you remember, on the frequency of the signal, depending of the amplitude of the signal. Let me say the speed of the signal. Let me say, roughly speaking, because amplitude, peak to peak, and also frequency both characterizes the changes. Let me say the changes. If do you remember, my lecture was always a constant. No, try to track a constant. If it's not a constant, yeah, we have some problems. We have, of course, we have some problems, and nevertheless, do you remember using the feed-forward action? If we if we place the eigenvalues, let me say, if we speed up the system using a state space controller, if we realize in the relatives fast resulting controlled system, we can nevertheless track also in a variable signal within a small bias. And we can reduce this bias, increasing, or realizing in a really fast controlled, excuse me, a little bit ill, system. Why that? Because I demonstrated that I can, with an integral, for instance, in robust form, this means independent of the parameter of the system, track asymptotically, and a constant. But what is the meaning of a constant in practical sense? This means that we simulate it also. No, we simulate it. This means that the reference signal, the signal which I want to track, is relatively slow, or much slower than the dynamics of the system. Which system? They control the system, because the reference signal is a signal which acts, which works for the control system. This means the trick is to include an integral which relies on robustness with respect to the variation also unknown parameter. Do you remember parameter R? I changed it in the simulation R, L. See again the presentation. The last part is correctly recorded. And in this case, with the integral, I can track asymptotically, but this is not a limit, because you remember speeding up the velocity of the control system, the dynamics, exactly. We can approximate this asymptotically aspect in a suitable way. I mean, the convergence remain asymptotical, but we can use nevertheless. We can use nevertheless. And about that, I told you many things. Do you remember when I told you the problem is very often the problem of the model? Is of course in linear model we have this exponential function solution, But in a linear model, in a linear system, and in the reality, I told you to remember this, when we have a friction, for instance, mechanical system, we achieve the goal in finite time. But this is not really a big problem because really we achieve in finite time, even though we calculate or we design everything in infinite time. The problem could be that I have a signal which is the signal which is not a constant, but very important in an engineering field that we can reduce this bias, which mathematically is there. I cannot achieve the track, the results or the signal which I want to obtain as possible results because of the bias. But we can reduce if the reference signal is slower, let me say so, than the dynamics of the control system. But that we can do that because we can speed up. If the system is controllable as we want, we can place, you remember, we can place the eigenvalues, let me say, where I want, where we want, such that the system sees the reference signal very slow, let me say, almost constant. It's not correct, this, but we can nevertheless reduce the bias. But let me now consider that we want to attain really a control system which minimize, let me say, which reduce to zero the bias, but not only, which achieve the goal in finite time. Extremely important. This means I don't want to accept this approximation to say I never achieve the goal, even though I told you it is a little bit a fictitious problem because practically we have losses which allow us to say we achieve the goal in finite time. But in any case, sliding mode control solves many problems in terms of robustness. We will see it's very used for this reason. But of course, we have to pay as in any method which allows to obtain some advantages. We have some drawbacks. Now we will introduce this topic, which is in control for robots in automation is extremely often let me say very uh, it's often used for its robustness characteristics. Basically, also to reduce the bias to zero, no, somehow indicates a robustness characteristic because independently of the changes, independently of the dynamics of the system, we can achieve this bias to zero. It's an advantage. We will see which kind of drawbacks we have, yeah, introducing the method. Let me open this file, which you can find in the electronic platform. Let me find 1 second. In the meantime, if you think that could be useful, you can download, but it's not necessary. It's an extremely easy introduction, which I like a lot, because I assume that not all students know this method or this technique. Isn't a technique, isn't a method. You can use both wording. 1 second now. Okay, I found it. 1 second. Excuse me. Ah, I upload and now I cannot find. Let me. I found it. Let me share now. Let me share. I hope you can see the lecture. It's a relative easy lecture. To introduce some elements of applied sliding mode control, because I try to avoid the methodological aspect, but of course I need nevertheless to tell you also something theoretical in the sense some equations. No? Look, here we can see directly in order to proceed a little bit faster that I emphasize the word robust. We can see that I wrote this sentence in order to focus on the robustness of this method. The method can be applied in linear and in nonlinear, for linear and nonlinear systems. We will see that the controller itself is a nonlinear controller. Please pay attention. The sliding mode control is nonlinear controller. And you remember, again, to repeat, a controller is a function of an error, could be complex, could be easy. Remember, you have seen P controller, PI controller. Until now, we have seen all, I think until now we have seen controllers. All controllers are linear controllers until now, are linear ones. Now, we will consider another controller, sliding mode control, strategy or sliding mode controller, if you want, which is non-linear controller, but can be applied for linear and nonlinear systems, also for linear. Why we say robust? We say robust because, as I told you before, we have seen that if we don't have exactly knowledge about parameter of the system to be controlled, or if you don't have about much knowledge about the dynamics, dynamics much more. If I don't want to include in the modern dynamics, of course, we have a uncertainties. You can see also another important keyword, uncertainties. And of course, ideally, I need a controller which is unsensible with respect to uncertainties, and unsensible or robust. There is a difference, but I don't want to go in depth, but it's clear. Unsensible is much more. Is much more. Unsensible is much more. It could be that during the lecture I will try to distinguish. I would like to distinguish a bit, but it's not important at this moment. Let me say robustness is more general, include also, I mean, unsensible is stronger. No? This means that the controlled system does not realize up at all if something is unknown, or if something is not considered in the design of the control. Also robust with respect to, look here, unmeasurable disturbances. We will see this also in particular. A disturbance is an input which I cannot measure, is an input which is not accessible. we have seen the accessible input is the output of the controller. A disturbance is a signal which cannot be influenced by directly by the controller. It's not something which I can measure. It's not something which is passing through the, let me say so, the controller. But this kind of method, or the technique, slide remote control, can really, under some conditions, manage very well the presence of uncertainties and disturbances. Look, I prepared for you, but not only for you, as I told you at the beginning, it's in a lecture which is included in another set or the sections uh, of another course. I selected here in a linear system, the easiest one, in a linear system, and the easiest one. Why is the easiest one? Because, okay, you can say the easiest is the derivative of x with respect to t equals 0, but not for us, no, because we need an input, because I have to introduce a control. I have to introduce a control strategy. This means u of t must be present. X of t, the state, about the state I told you a lot. At this moment is in a scalar. U of t is the control signal. I clarify why we need the control signal. X at time 0, x0 is the initial state. Please pay attention. What is the problem? The problem formulation. The goal is steer the state to 0. Look at these obvious strategies. Again, fix the goal. X0 is not 0. I want to find an input u to steer the state to 0. I want to find input u which steers the state, which is not 0, to 0. Look, in case x of t positive, starting, of course, from x0, no? For instance, positive. No? But, of course, why I'm writing x of t? Because I want to find the u of t. I mean, x0 larger than 0 is also a starting point. But of course, if x on 0 starting at 0, larger than 0, the x with respect to the t less than 0 works nevertheless. I mean, at each time, also at the beginning, at time 0. If I have a state positive, I try to find the u of t which realize the derivative of x negative. Vice versa, if x of t is negative, I try to find a u of t which increase the x of t. This means the derivative is positive. Easy. If it's, x of t is positive, I have to decrease x of t. This means the derivative must be negative. If x of t is negative, I have to increase x of t. This means I try to find an u of t which realize in a positive derivative, no? Because the idea is to increase x of t. It's obvious. No? If I have too much, I try to reduce. If I have too less, I try to increase. This basically is the roughly translation of this strategy. Therefore, I called obvious strategies. I am looking for u of t. Look now at this state controller, because we knew, or we know, this state controller. It's exactly what I told you until now many times. No, it's a state, we call the state space controller. Do you remember? But in some books, state controller. No? But of course, it's a state space controller. It's exactly what I told you until now, a part of the most important part, no? The state space controller, or the state controller is it was always present. At the end, we concluded the first part of the selected topics. Consider it a state space, or the state controller, and integral control in the context of the state space or the state controller. Do you remember? Look at the last part of the lecture again in YouTube. K positive. Do you remember? Exactly. I am considering this because is a continuation, of our lectures. Idea is that using my controller, I have to realize at the beginning asymptotically, exactly as I did until now. No? It's not in a particular task, because until now we have seen, you remember, t toward infinite, always asymptotically. We are speaking about asymptotical stability, we are speaking about asymptotical convergence. Exactly until now, we did just analysis asymptotically. We reconsider again this. No? So it's familiar. Look, if I close the loop with this state controller, which we know, we have this easy differential equation. You are probably better than me in math, in analysis 1, analysis 2. The solution of this differential equation, linear differential equation, k is positive, please consider x at time 0 equal x0. You see, I didn't repeat, but I told you. The solution is one at the end of the slide. I don't know if you remember, but if you don't remember, you can calculate, or in any case, believe me. No? We can see that I steer, or if you want, I control the state starting from x0 to 0 asymptotically. If x0 is positive, we have a profile which remain, or the function will remain always positive and is going to 0 if t is infinite. If x0 is negative, we are on the, let me say, lower part of the x-axis, and we remain negative, and for t infinite, we go into 0. Easy. Look, what happens now if I modify a little bit my state space controller, my linear state space controller? I modify this nonlinear control with this nonlinear control, in which u of t is not minus k multiply x, but minus k multiply sgn of x. What is sgn? I don't know if I have it here now. It is, but it's an approximation. Let me tell you, and probably I will show you with the lateral camera. SGN is sine of x. I told you at the beginning of the course when I told you about the friction force. Do you remember? SGN is 1 sine, signum in Latin. SGN of x of t is 1 if x of t is positive, is minus 1 is x of t is negative, is 0 is x of t is 0. Let me see if I have a picture so you can focus directly. Let me, I have here in a folder. Just shortly, if I find quickly, otherwise I can also, I found. I can also draw a result. It takes 30 seconds. It's a nice function. Let me share. Look, it's this function here. 1 if x is positive, minus 1 if x is negative, 0 if x is 0. It's a shame it's not written here because I considered now SGN of x circa hyperbolic tangent of gamma x, because very often we try to approximate this sigmoid function. SGN, exactly this function again. 1 if x of t is positive, minus 1 if x of t is negative, 0 if x of t is 0, is an ideal function. No? First of all, it's not continuous function. Very often we try to approximate, to realize with microcontroller, also sometimes in Simulink to avoid some problem due to the not continuity. We will see probably in Simulink a little bit together. We try to approximate with function like hyperbolic tangent or 2 divided by arcotangent. In this case, hyperbolic tangent and arcotangent, both are sigmoid function. Very important gamma, no? This argument gamma realizes basically in a good approximation. We can see here, larger and larger gamma, we have a better and better approximation of the SGN function. We don't use often because it could generate problem because of the non-continuity. I mean, for x around 0, we have to switch between -1 and 1. It could generate some problems. Moreover, for some application, it's not we cannot differentiate this function here, the SGN. SGN, let me see if I have to be more clear. I don't think it's clear what I intend. Let me see. Yeah, I have it. Here's a function of omega. It doesn't matter which kind of argument I have, no? I don't know if you remember this concept here. I already introduced in the context of Coulomb friction when I told you about, I don't remember, the car movement or the aerostat, something like that. -1 if omega is negative, 0 if omega is 0, 1 if omega is positive. It looks like something like that. This S function, sigmoid function, is the ideal function. One second. Let me put here because otherwise I lose everything. Okay, let me switch now. Yeah, let me modify our well-known state space controller with this nonlinear control strategy. Now, we have a differential equation, which is nonlinear differential equation. The controlled system is here. The x with respect to the t equals minus k, which multiply SGN of x of t. X of t, the solution, now is x0 minus kt for x positive, and x0 minus, x of t minus x0 plus kt for x negative. Why that? If you do the integral, considering that SGN is 1 or -1, depending on the sign of x of t, is quite clear. That is this one. The reason is, think about if I do the integral of the left part between 0 and t, and if you do here again the integral between 0 and t, it's quite clear this. I don't know if, because on the left part we have x of t minus x0 equals minus k of t. I don't know if it's not clear, I can do very quickly in order to. Probably I don't need to. Typically, we change the variable here. Here we have equals. No? We have the integral of the derivative. The integral of the derivative. Please pay attention to tau t, but just in a formal thing, no? Not only formal, but and here, if you distinguish, let me say just quickly positive, because at time zero, at time zero is zero, no? To remember this, x at time zero exactly what the let me see. I avoided the other one just to sketch um, just to sketch here the first one. And I can write in this form here, just thinking mm, that if you consider this here, this is positive, and from if you consider x0 minus kt larger than 0, I will obtain from this condition that t is less than x0 divided k. Also, considering this equation here, I do the same consideration. This means this part less than 0 implies that t is less than x0 divided k. This is extremely important, this last condition. I don't know if it's clear, no? I put this larger than 0, and I will obtain that t, in case x of t is larger than 0, we have this solution here. This implies that t is less than x0 divided k. I do the same calculation in the second equation, and I will obtain also that k is less than x0 divided k, meaning that we have this condition here once for x positive, once for x negative, which says basically that we obtained x of t equals 0 at t equals x0 divided k. At x0 divided k, in fact, if you substitute here and here, we obtain exactly 0. I put absolute value because it works for x positive, x0 positive, and for x0 negative. We can see uh, a little bit what I intend. And when I obtain 0, of course, the sign of 0, as I told you, is equal 0, and this means no changes in the system. This means I will remain. I will remain there. I will remain there. Basically, I summarize everything with the last equation here. If assuming that x0 is positive, no? Just to show you one. I don't know if I have the other one too. Yeah, just graphically. Exactly what I told you now. I summarize in this form here. For t larger than this, I remain to 0. Why that? Because the derivative of x of t is 0. Graphically, we have this situation here in which I calculated just for the positive. I don't think so. They have a negative. I have also negative. I also negative, but the negative analysis is exactly the same. No? If you want, I can repeat a little bit here. I summarize directly the negative analysis, considering this function here in case x0 is negative, but this condition remains the same. No? This condition remains the same. And when I achieve 0, x of t remains 0 because the derivative of x of t remained at 0. Remained at 0. Let me coming back to repeat a little bit because was a little bit too fast probably. But now, again, very quickly, very important is because we have seen that we achieve the goal in finite time. Therefore, I would like to repeat a little bit. let me say, um, the idea. Let me see if I forgot to say something. I don't think so. Yeah, let me repeat again quickly. Um, the differential equation of the x with respect to the t equal minus k sgn of x of t. If I do the integral, assuming that sine of 0 equals 0, no? And in accordance with the definition, nevertheless, I have uh, this solution. And yeah, here is easy to calculate. Let me from this information here, I will obtain this because this expression is larger than 0. I can calculate that t is less than x0 divided k. I do the same for the negative. Very important in both cases. We obtain that t is less than x0 divided k. This means between 0 and x0 absolute value, because independent of the sign of x0, we obtain the solution. But in particular, we can say that it's 0 for t equal x0 independent of the sign. Therefore, I put absolute value divided k. At this time, the derivative is 0 because Sgn, in accordance with the definition, of course, mathematical definition is equal 0. I can summarize everything in this form here for positive and negative. Very important, the graphical representation, which we can see that at time x star, which is x0 absolute value divided k, we obtain the result. Very important at finite time. Again, this x star is this here, which can be designed considering different k. If k is a parameter of the controller, do you remember? Until now, we have seen in our analysis that k is a parameter of the controller. This means also I can put whatever I want, let me say in this form. No, I can design. I can design. This means I can obtain my goal in finite time, and more, I can choose at which time I will achieve the goal. Look at this last sentence of this slide. If you remember my previous slide, I tried to approximate the SGN with hyperbolic tangent, with 2 divided by arcotangent of, in both cases, gamma x, no? In which gamma is a constant to approximate this SGN. Here, we use a similar approach. No? We approximate SGN using a saturation function. You can use whatever you want. No? You can do whatever you want. The saturation function probably is known from different courses. Basically, between, let me say here, -1 and 1, in which, in this case, phi is 1, which in this case phi is 1, or in general, you can consider phi another value in this sense, change the interval here, the interval of the approximation. Basically, in this particular case, if we have an interval in which we have a linear function which approximate, let me say, the SGN. Basically, the approximation is of course around 0 because it's the point in which we have the critical condition, the non-continuity of the SGN function. This is the approximation. The name is the saturation function, which in general, we can see here that we used a phi, the name is thickness, of the boundary layer of this interval, which can be also designed. Very often we use hyperbolic tangent of gamma x. Let me see. If I forgot to say, yeah, with phi, we defined the interval here. Yeah, exactly. X of t, excuse me, probably I didn't explain correctly. In this case, x of t equal phi is our boundary layer, and phi is the thickness. We can define, we can put whatever phi. Of course, if I put phi equal to, we have a larger boundary in the sense in which I will approximate the SGN function. We use very often the hyperbolic tangent or 2 divided pi arcotangent because we try also to avoid this point here, which could be a problem because anyway the derivative is not so the derivative is continuous here. But anyway, you can use also this one. The problem is to avoid the discontinuity at 0. Okay, let me see if I forgot to say something. I don't think so. Let me now go ahead thinking that what happens, you remember I told you a lot about the robustness. I told you a lot about the robustness. This means, let me analyze what is the meaning of this. Assuming that the equation is not exactly the x with respect to the t equal u of t, but we have a part which I don't know exactly, but I know the upper bound, absolute value of this delta, which can depend on x, can depend on t, can be everything, could be an uncertainties, which something which I don't know of the model, but could be also a disturbance. Could be everything. Yeah, it seems to be something which depends of a, but could be everything also in this form here. Disturbance uncertainties less than delta x. Delta max is the maximal value. If I don't know, I can overestimate. Anyway, I have the upper bound. Or better to say is upper and lower bound. No? Is bounded. No? The bound, I have the bound. That is correct, I said. Now, if I apply my state space controller as I did until now, I put u of t equals minus k multiply x here. The strategy one is the strategy which we use until now in the first part of the course. If you remember a little bit the differential equation theory, we cannot steer the x of t to 0 as long as this delta is not 0. I don't know if you remember, because the solution depends on this. I don't know if you remember. I don't have here many calculation. I try to avoid it. But of course, let me consider if this is 1 and a constant, 1, just to understand. In fact, I told you I will not obtain x equals 0 as long as this is not 0. Example, if this is 1, what is the solution if this is 1? The solution is x as before, x0 exponential function up to let me show you here. Quickly, you can verify also this element is 1. Just to give an example. Of course, the initial condition is always the same. Try to think. hmm, This was the solution of the homogeneous. I'm not sure about, probably I have to calculate now. Let me see, 1 second. Let me recalculate this. In any case, I have this as a persistent element. We can see here. No? About this, I have to calculate. I was too fast, probably, but I can do. This is in constant C, because this here is the homogeneous. You remember in math, no? As before. Now I have to calculate C with this condition. This means it's not exactly as I told you, but similar, no? Yeah, excuse me for the error, but now should be correct. If you remember, it's not the program of this course. No? Just to be precise, you are better than me, I am sure, in math. But what I want to show that is not zero for T infinite. No? Very important, this component. Again, this part here is the homogeneous solution of this differential equation. I have to cancel this. No? With the C, all possible homogeneous solution. This is a particular solution of the non-homogeneous. You can substitute. We have directly that this is the particular solution, a particular solution of the non-homogeneous. And then to calculate this C, I have to consider this. No? I hope no mistakes. Let me see again. It's too fast, the solution. Let me see. No, I think it's okay, no? Because I put here x0 at time 0. We have this. And this I can calculate C. In fact, this solution here at time 0 is x0. And then just to complete, no? Now we have format a little bit. At time 0, x0. And then, but it's not 0. No? This is something which depends of k. Of course, for k large, we convert to 0, but it's never 0. No? For k finite. Just to repeat a little bit math. This means with our, what is the idea in this course? Please, this mathematical aspect is not extremely relevant for us, but we can say now that our approach does not allow us to steer the state x0 to 0 even in infinite time. I show you for a constant. Therefore, at the beginning, I told you as long as delta x of t comma t is not 0. I did just an example to understand better. Let me go ahead here in our approach. Let me consider now this nonlinear strategy. No? Instead of x of t, I put SGN of x of t. Now, do you remember I told you we know the boundary of delta? K larger than delta x is an impossible assumption because the idea is to overcome somehow. We discuss later why we choose k larger than delta x, delta max. This boundary, assuming that is bounded. That is not a conservative assumption. It's a disturbance or is the uncertainty. It is not bounded. We cannot do anything. Not bounded means infinite mathematically. This means k is larger. That if I choose k larger than delta max, I can consider k equal delta max plus eta, in which eta is positive. We can see at the end of the slide. In some literature, we can find denominator minimal convergence speed. The minimal convergence speed. But anyway, K larger than delta max. From the equation 1, for x positive, I can write this. What I did here, basically, I replace K with delta max plus eta. No? Easy. Just plug it in here for x positive. For x negative is this one, because sign is -1. Easy. I repeat it again here, this element, in order to have in mind. What I did now in the middle of the slide, I put on the left part, I move to the left part, the element delta max, which I have here, and delta x, comma t. No? We can see, in fact, it's the same expression, but we have on the left part plus delta max instead of in the right part minus delta max. Instead of plus delta max, I have a minus delta max now in the left part, equals minus eta. Basically, I moved, no? Do you remember this rule in the high school? I moved from right to left some elements, in particular delta max and delta x, comma t, but I have to consider their sign. No? I do for x positive, for x negative. Now, please pay attention here, extremely important, this trick. We know that delta max minus delta is larger or equal to 0. No? It's equal 0 when delta is exactly delta max, but it's larger because delta max is the upper bound, let me say. No? It's the maximal value, no? The maximal value. And in the same way, I can say that delta max minus delta is negative or equal 0. Independently, here we have to add independently of the value of delta. Always, no? Because we have the boundary for delta. It's the maximum value, clear. This means the first equation, which you have here in the middle, becomes this. Why become this? Because I am subtracting on the left part something which is positive. I don't know if it's clear. But here it becomes larger than eta for x negative, this part here, because I am adding on the left part something which is negative. I eliminated, let me say, something which is negative. I am, eliminated something that is negative. Again, this here, excuse me, I made a little bit confused, but it's correct. This here becomes less than or equal eta, or the minus eta, if I don't consider this element here, because this is positive. This means now as if I subtract. And here in the same way becomes larger because as if I added something positive on the left part. And here I subtract something positive. I repeat it again, this result. Look now what I am doing now. I multiply, as is written here, left and right by SGN, these two equations. At this moment, nothing to say. I multiply these two equations by SGN of x. Now, I repeat it again here, these two equations. And then look what I am doing. I repeat it, but considering that here I have x of t positive, this means +1 instead of SGN, or the plus just. +1, you can say. And here for x negative, we have a -1, because SGN and on this part is -1. If I multiply now by minus this equation here, I have this. This means both equations for x positive and x negative, x of t positive, x of t negative, can be represented in this form because they have the same expression. Do you remember eta was this minimal convergence speed, which in some books can be seen as a reachability condition, but it's a parameter. No? Very important, larger than 0. very important larger than zero. Here is not written, but here yes, no? Because otherwise the hypothesis was, yeah, here, K must be larger than this bound, the maximal value of the unknown part. I didn't repeat it, but it remains. Look now, what we have for eta positive, no? We obtain this reachable condition. The meaning, eta reachable condition means that we obtain zero in finite time. Why that? Because this equation here is the same which we had in the strategy 2 at the beginning, even though I am considering here disturbances. Look, this equation here with the parameter eta instead of parameter k, which we'll obtain at the end of this. But it doesn't matter. Eta and k structurally are constant, which I can design positively. This means I will obtain, even though in the presence of disturbances or uncertainties, my state to zero in finite time with the same condition as before. With the same condition as before. This means in this case, the condition is t star instead of x0 absolute value divided k is x0 absolute value divided eta. Let me see if I can say something more quickly because I need to speed up a little bit. 1 second. If I find directly here. One second, huh? I have to speed up a little bit. Look at this. We have seen this before. For t larger than t star, we are at zero because the derivative is zero. Now we have this. But we have the condition or the relation between eta and k. I don't know if you remember. Eta can be seen as k minus delta max. I don't know if you remember this. Because k was equal delta max plus eta. I don't know if you remember. K equals delta max plus eta. This means eta equals k minus delta max. This means now, if you compare this expression here with this expression here, we can see, but it's logical in the sense that in case of disturbance, this is the price which you have to pay. We need more time to achieve zero. For and in this sense, we can see because, but this is you can see here. No? K is always larger than delta max. No? It's clear. The reason is that we need time. We need time to overcome. Intuitively, we can say so. The disturbance which we have. Let me see if I can add something. Mhm. Um, How I can obtain the same time? I have to increase the parameter. If I uh, increase the parameter k, I will obtain the same. This is the price, basically. Let me see if I forgot to say something. Scriviamo also from here, no? Just to compare. K equal delta max plus eta. But intuitively, no, I think we don't need now to do that exactly. But of course, if I have a disturbance, to obtain the same time of convergence, I have to increase the parameter k. This is the initial form, no? We have a price. With and without, we have a difference. We need larger k to obtain the same convergent time. Otherwise, I have to wait a little bit. But in any case, this eta must be positive. No? Otherwise, we don't have this reachability condition, data reachability condition. In any case, you have to overcome this delta, delta max. Again, this must be positive, strictly positive. Of course, if delta max is not there, this means we don't have this uncertainties. Theoretically, I will converge with very extremely small, infinite small k, no? Infinite small k. Of course, I will converge infinite time in this case in infinite time. It's a little bit in the contradiction because I am including infinite small k. But mathematically, it's easy to understand. But let me remain in concrete case. No? Concrete case say k should overcome the disturbance, and I can short the time, convergent time, increasing k is easy. But of course, this is the price. Let me present this case. Oh, I think we can take a rest, I think. I think this is better to take a rest a little bit because, yeah, I didn't realize it's 10 before 3, yeah. I would like to take a rest here, let me say 15 minutes more or less. I drink something, and then we will conclude this part. And then today, nevertheless, I do an exercise, no? I will do, this means, but we have time. 15, maximal 20 minutes, and then we will see here. Thank you again. Uh, Let me, before restarting with the presentation, let me, it's not a clarification because it's extremely easy, but let me reconsider this equation here because once I receive a question, yeah, it's clear, no? The integral of a derivative is basically is the function x, the derivative of x calculated at this point minus the function x calculated at this point. And student once I asked, of course, this is for x positive, no? And then we can do the same. I mean, this result, to be precise, this analysis for x positive. Otherwise, do you remember, for x negative, we have to consider the sign a little bit. This means in this context here, look again where this comes from. We have to distinguish two cases. In this context, what happens at time zero? That we have a sign of x0, but if x0 is positive, yeah, in any case, on the right part, we have a k. This is a little bit what we have to consider. K multiply t in the sense. Let me now open the lecture and let me consider this case. Now, why this case? As I told you, the system, how possible to say, yeah, with just one state is extremely limited. With two states, as I told you probably at the beginning of the semester, we can also approximate some complex systems, because a system of two states, probably you learn in the math, the system of two state can oscillate, the system of two state can represent large behaviors in this sense. Let me consider the easiest system with two states, x1 and x2. Basically, can be considered this here a mechanical system, if you want. We have seen, but not only. We can consider also electrical system if you think about, for instance, mechanical system, x1 could be the position, x2 could be the velocity, and here we have the acceleration equals the force divided the mass, which in this case is equal 1. Otherwise, x1 could be, for instance, the current. X2 is the voltage on the inductance, divided, of course, the inductance itself, and so on. No, we can consider, of course, different system. But let me remain eventually, if you want, with the mechanical system. Look at the end of the slide. The goal is always the same, no? The goal is always the same, to steer the initial states, x1, 0, x2, 0, we can see here, which I compress in x0 to 0. Look at this, at the last part of of this slide. Let me assume that I can consider a controller x2 of t equals minus c1 x1 for c1 positive, and the derivative of x1 with respect to t equals minus c1 multiply x1. Meaning, the meaning is the state x2 is proportional with minus, of course, to x1. And then I plug in here. But the key point is this: x2 is proportional to x1. It's something new, if you think, because until now, we have seen in the context of our controller that we don't have this proportionality between states. We never see. We have seen that U, for instance, is a combination, a linear combination of states. I don't know if you remember. This means x2 proportional to x1 is something new. C1 is positive, no? For instance. Look at this. Assuming that this is acceptable, in the sense it's possible control. Then we have the x1 derivative, the derivative of x1 with respect to the t equals minus c1 multiply x1 for the second, consider this equation here, and for the first equation. Look here, if x2 is equal minus c1 x1, if I plug in here, I have the x1 with respect to the t equals minus c1 x1, exactly plugging in this equation into here. Exactly this equation here, c1 again larger than 0. The solution of this is clear. We have seen also today in a couple of times. This means x1 is going to 0 if t is going to infinite, and x2 is also going to 0. Why that? Because it's proportional to x1. Clear, no? The conclusion. Please remember that x2 is proportional to x1. This means if x1 is going to 0, so x2 is going to 0 in infinite time. Good. We have something similar as before. Do you remember? Before we had the proportionality of U with respect to the state here is a little bit different, but anyway, it seems to be that with this assumption, and of course, if you look here, we can see also the condition of U, we can work. But, and then we will see later this. But what is the problem here? The real problem is this assumption here, x2 proportional to x1. Physically, let me reconsider again the example of the mechanical example. It's not so easy to obtain, because this could mean, I would like to say, that the velocity is proportional to the position. How we can realize this physically, for instance, but also in other contexts, in an electrical system, it's extremely difficult it's impossible physically, mathematically, of course. This means the idea is good mathematically, always thinking about to achieve the goal asymptotically, first goal. But practically, the x2 equals minus c1 x1 is not possible to be realized. We have seen, for instance, the example of a mechanical system, how we can obtain the condition in which, as is here written, that the velocity is proportional to the position. Doesn't make sense. Increasing the position, this means I will increase the velocity. You understand that mathematically I can do everything. The second idea is to realize this condition, x2 equals minus c1 multiply x1. Let me say indirectly. Now I will clarify what I intend, because the idea is good in the sense to achieve the goal in infinite time. Look at this last equation of this slide. S of t equals x2 of t plus c1 x1 of t. Now we can see what we have behind this equation. If I'm able now to steer x2 s of t to 0, we have exactly the condition. Because if s of t to 0 means x2 equal minus c1 multiply x1. Exactly what I told you now. It is written here. And now we don't realize that directly, but indirectly, what I intend I will show you in 1 second. The goal at this moment is to steer the system at st equals 0. Here I recall the system on the right part here. If I differentiate s of t, we obtain this equation here. S of t again is x2 plus c1 x1. But look, if you reconsider the system, we can see that the x2 with respect to the t is u of t, and the x with respect to the t, x2 of t. From the first equation, we have a c1 multiplied x2. From the second equation, we have a u of t, because the x2. This means we have now the possibility to realize the u of t, which we can see here. No? Why that? Because if I put the s with respect to the t equals minus k sgn s of t, now we know why we need this equation here, because this equation here realizes in finite time s of t equals 0. Now, please pay attention. The variable here is s of t, which depends in our case on x1 and x2, but the argument is s of t. But this structure here, we have seen many times that realizes s of t equals 0 in finite time. And now we have also u. Why that? Because look here, this part here, which came plugged in the system here in the derivative of s of t, which we need to obtain this is the equation here. It's basically here. And u of t, what is u of t? Is minus u1 x2 minus k sgn or s of t. Now, this u of t realize s of t equals 0 in finite time. And when we have s of t equals 0, we have exactly our condition which allow to say I will achieve the goal in finite time. But what is the advantage is with respect to before? But yeah, it's clear. Yeah, it's clear what u of t is. Basically, the problem is to realize and to calculate, to realize the concrete form of u of t. The concrete form of u of t, which can be realized. It is. Because this part, we have already seen that it's possible to be obtained, is u of t. We have seen many times the switching function and the SGN function of something. And, please pay attention, proportional to a state. This means this u of t is something which we know somehow. This part here is known from our preview lectures, proportional to the state. And this part here is proportional to the SGN of something. It doesn't matter which one. In any case, this is +1 or -1, depend of s of t, if positive or negative. But when we achieve s of t, please pay attention, in finite time, we obtain this. And this allows to say that I will obtain 0 in infinite time. But now the goal is we have an u of t which can be realized. Here we have a graphical interpretation, starting from initial point, we will achieve s of t equals 0, we will obtain, do you remember this line here, x2, do you remember, equals minus c1 x1, no? Represent s of t equals 0. Starting from initial point, I will achieve this point, and then I will, through this line, go to 0. Of course, here we can see the visible switching, because practically SGN switch plus minus k when we are in the positive and we are negative, let me say, region with respect to S. Everything which is larger than S equals 0 in this region here. Everything is less than S equals 0 in this region here. And then I will switch just to figure out what happens. We have an enriching phase in which we achieve exactly our S of t equals 0. We achieve this in finite time. It is read also as we had. Do you remember? At the beginning of the lecture, we had the initial condition, in this case, the initial conditions divide k. No? the initial condition with respect to S, no? Because the differential equation is in S. Please pay attention. Therefore, we have here C1 x1 0, because the initial condition with respect to S, the differential equation is in S, because the first goal is to reach the surface S of t equals 0. Then I will go ahead with Chattering phenomenon. I will simulate for you in order to understand better. Until x1 equals 0, x2 equals 0, but in infinite time. We have a part with finite time convergence, and we have another part with infinite time convergence. Of course, we can also modify the system in order to obtain also the second part in finite time. I don't know if I have time to do. It could be that I will do in an appendix, but let me go ahead now. If you remember a little bit this saturation function, which we approximate the SGN now with this thickness. This means we will define a region in which around this region I don't switch. To remember this behavior is linear. But outside I will switch outside from this phi, this thickness. Very often we use as I told you, hyperbolic tangent because yeah, it's a continuous function. In this sense, as I told you, we don't have an area switch. No? We have a soft switch. In any case, when we used an approximation, so this one, we don't have a switch. We have a soft switch in the sense. But using a hyperbolic tangent or 2 divided pi arcotangent, we have a more soft switch. Look at this information here. The beginning is the same differential equation, which I told you a lot. If I multiply this differential equation by S of t, we have the equation in the middle. And look at this equation here. This equation here says that we have the derivative of a positive defined function, a positive function, let me say more roughly speaking, S squared is a positive function. Surface, we call the surface. The derivative of this multiplied by 1 divided 2 is negative. Because do you remember, x multiply SGN of x is absolute value of x, no? Here. S of t multiply SGN of S of t is absolute value of S of t. I don't know if you remember. This condition here is the Lyapunov condition, which I will tell you now, but I would like to say directly with an example, without let me say, considering the theory, because my idea is now to show you an extremely easy example to recall this concept of chattering, switching, and so on, but using an easy but concrete example. But in the meantime, introduce this Lyapunov, or already introduced the Lyapunov condition, but more in a more formal way, using an example which I would like to simulate with MATLAB Simulate. Let me stop a little bit the lecture to look at the material, because during the pause I was not able to check because I was called by some colleague. Look at this example now, in which we will reconsider what I introduced, in particular, the Lyapunov condition through the Lyapunov theory. Look at this extremely easy example in order to understand. X dot equal minus x squared is I put x0 because one student asked me, and then I will tell you later when I open MATLAB why this is 0. Plus 2 times u of t, of course, plus the disturbance You remember I told you that the method is strongly characterized by a robustness or insensibility with respect to disturbance under conditions. I show you what I intend. This is basically the system. Let me consider that I would like to uh, obtain a desired trajectory x of t, r of t. This is interesting because could be a point, uh, could be a trajectory. Trajectory is in a set of points. This is the goal. Do you remember? Until now, we have seen this is not new. R of t at this moment, most of the case was in a function and a constant. You remember? But at the end, we tried also with the sine, cosine, and I told you could be also an R of t. Do you remember using in a feed-forward action? Anyway, if you look at the slide, at the yeah, at the PDF document, we can understand that I can consider also a signal. Let's consider here now the second theorem of Lyapunov. I don't have time to tell you about the first. Yeah, I would like to tell you the first theorem because uh, you know that I have a lecture here in UC on dedicated to um, the lab in which I sketched the first and the second theorem. I will reconsider this lecture, I think, next week or after next week. I don't know if you already attended these classes in the lab. It should be in the repetition, but we will see more in depth the concept of the sliding, the sliding condition, which in the lab I didn't emphasize. But let me consider now direct this Lyapunov method, which is the second method, in some books is called the second, in which we will see these Lyapunov conditions, which I introduce in the slide. I will come back in the slide in a few minutes. To solve this problem, to track a point, or to maintain the system in a point, or to track signal, the track signal, we know what we understand, what we intend. A desired trajectory. Even in the presence of a disturbance, and we will see with the simulation, even in the presence, also with the calculation, with unknown part of the model. We can understand better now with concrete example. The theorem says, yeah, I forgot one point, but it's implicit. Positive function. Do you remember s squared? Remember? Now we come back. At my goal, zero is the goal. When I achieve x equal r of t. But yes, the theorem says about a zero. No? The goal is zero. It's not so strange to speak about zero because until now, in the first part of the lecture, do you remember, the goal is to steer the state to zero. The mathematicians say always zero is the goal. Of course, if here the goal is x of t equal r of t, the goal is our zero is r of t. I can clarify better in a few minutes. Second condition, the derivative of v negative. Here I forgot, but each time I will say the derivative at the goal equals zero. Basically, something like that, in which I try to obtain using a u of t a manifold and a structure of the control system in which my zero, r of t, is an attractive point. It doesn't matter where I am. I will fall down in this zero here. Of course, it could be more or less attractive. You can see here this curve or this curve. But in any case, it doesn't matter where I am. I will fall down here. Could be also in trajectory, of course. Let me show you graphically what is the problem or the representation with the trajectory. just to understand. I don't know if you can figure out. It doesn't matter where I am. I have a structure which includes the control law, which converge. We will track this. I will clarify a little bit better. Just now, figure out what happens. It's easy, the example. It's easier than to explain. Look, let me consider the easiest S of t, the error, between error of t and x of t. The easier surface, sliding surface. Lyapunov function candidate. Is positive? Yes, it's positive. You remember, we have to obtain that the derivative of this positive function is negative. It's also written here. I show you this indirectly in our case. Now, with the theorem, we can understand this condition, where this condition comes from. And much more. Oh, here it's more structured. The example which I presented was just an introduction. But let me see. So, is positive? Yes, it is. At our goal, x equal r of t is 0, it is. This also guarantees. By definition of my Lyapunov candidate, we say that in a function v of s, which in general v of x, all state must be represented. Otherwise, we have a Lyapunov-like. It's not exactly an orthodox Lyapunov function. Here, we have just one state, no problem, no problems. If all these conditions are guaranteed, we say that we are in the presence of a Lyapunov function. At this moment, this is a candidate. This is guaranteed, this is guaranteed. What about this? This should be guaranteed using, in particular, U. This is the constructiveness of the system, of the method, because I can calculate U such that this is guaranteed. This, we will see, is implicitly guaranteed by the choice of the Lyapunov function. I show you the derivative of this. Do you remember? Must be negative. In our case, we verified the Lyapunov condition because was equal k minus k multiply absolute value of s. Look at this. The derivative of this expression is this one. 2 divided 2, I will cancel. Therefore, historically, we put 1 divided 2. No meaning here, no meaning. S multiply S dot, S multiply, this is S dot, clearly, no? The derivative of this. At the beginning, please don't consider D, or at least D equals 0. This means the system becomes this. Please pay attention. I didn't tell you, but it's visible. No, it was visible. We are in the presence of a nonlinear system. X squared. Now, if I plug in this expression here, I will obtain this here, no? If I put equal 0, it is not exactly our goal, but it's almost our goal. I will obtain an equivalent function for U, U, which I call equivalent, with guarantees that this is 0. This means somehow, as I told you, we are close to our goal, because now the derivative is 0, but not less than 0 yet. Not less than 0 yet. But if I add now this switching part, the name in some books is corrective. No? Now we will obtain. But now it's easy to justify, because if I consider U of t the sum of both, if I add now to this here, this part here, we have basically that this is the control law, and substituting u of t, which is this here inside, excuse me, here inside, this expression here inside, we will obtain, let me take another slide. Just this one because the rest is cancelled. But as I told you, S multiply SGN of S is absolute of S of t. Of course, it's negative with the condition beta, but beta is a design parameter. I can choose it. Beta positive. We have this negative. This means also the second condition is guaranteed using this control law, which we can see depends of the system, depends of somehow on the reference value. And of course, we have a switching part. Now we will see what happens if D is not zero, but let me show you another thing. You remember I told you sometimes I forget to put this because it says I told you, as I told you, is automatic guaranteed by the choice. Look here. For S equals 0, here is everything in S. No? We have exactly that derivative for S equals 0 is 0. S equals 0 means at go. The derivative, excuse me, the derivative of V at S equals 0 is 0 because this is 0. No? Therefore, I told you sometimes I forget because it's implicit in the choice of S. Very important now to look at D. I have also a better explanation. It could be that I will write here if you want. If D is not 0, but limited, it is enough to choose beta larger than the maximal value of the disturbance. Now, I would like to show you a little bit better than this. This is basically, I didn't clarify why. Let me write here for you. Assuming that we have a disturbance, and assuming we have an error in the cancellation. Why an error in the cancellation is important to be considered? Because this U equivalent can sell everything which we have here inside. You remember I told you I calculate U equivalent considering equals 0. This is not enough. But in any case, we have to consider what happens if the cancellation is not perfect. And what happens if I have a disturbance inside. The solution to this, we have to consider the beta larger, we have seen before, than the upper bounds, let me formulate so, of our uncertainties. Let me show you a little bit better. This means here inside, I don't have just this one. I have a delta x of dt. We have seen also this expression here, no? Plus d of t, because we have something which remain inside if the cancellation is not perfect. It's not 0 here. It's not 0. We have something which remain because of the cancellation is not perfect. We have a disturbance, which until now we didn't consider. But we know that exists a solution. Do you remember? I told you theoretically that, do you remember this solution? This solution came from this theoretical analysis. Beta, at that time I called K, this coefficient, the switching coefficient, the coefficient which multiplies SGN, large enough. We overcome all possible uncertainties. Beta large enough, we overcome all possible uncertainties. This and this. Let me show you. a little bit better. Let me put in evidence beta here. Did you agree, no? Math from Ginnasio. I didn't change anything. Now, please pay attention here. If beta larger than, of course, the condition is conservative. This means it's not necessary, but it's enough. It's not necessary, but it's enough. Of course, here, it's just this one because I didn't consider any cancellation errors. But yeah, more general, no? If I consider this conservative as such, which is not necessary, but it's enough if we have this, no? What I can write here? I can move to, it is better, no? Less or equals, in this sense, is strictly large, less, no? Give me 1 second. Let me, in order to be clear, let me write beta star. No. No, I consider a particular beta larger than this. No? This is the meaning. Let's consider a beta star larger than this. I write again this. Now we can do some consideration extremely interesting. Why that? For S of t positive, what we have? This is 1, but this is independently of this numerator. This is always less than 1 because of this. Clear? This means this is positive, this is negative. Do you agree? Perfect. We obtain this Lyapunov condition, which I told you in the theoretical part. But similar consideration can be done for S negative. Let me show you. If S is negative, this is negative, positive, right? This is negative with minus positive. Independently of what happens here, this is always less than 1 or larger than minus 1. This means this is always positive. I don't know if you agree. In absolute value, this is always less than 1, always, because of this. But this is negative. This means again, this is positive. multiplied by negative, we have something like that. The Lyapunov conditions are guaranteed. Large enough, of course, it could be that we need less than this, but this guarantees is enough, but not necessary. The last consideration on this disturbance, and then we simulate. We simulate. Look at this. Look at this sentence here. Theoretically, we can reject the disturbance totally. This means we are insensible with respect to the disturbance when we are moving on S of t equals 0. And the question is, how is the disturbance compensated? It's quite clear here, and now we can justify very well, that the disturbance is compensated, perfect compensated on the surface. Please pay attention, on the surface, yeah? Just on the surface, when basically I switch. And we have that the corrective time part is exactly minus d of t, because it's in a cancellation of the disturbance. This can be used also as a proper possible identification of the disturbance. Let me discuss a little bit this. But why that? Yeah, because if you think um, let me see how possible to justify better. Let me see how I can justify. I think we can see just quickly, you can think that is the unique part without disturbance. Without disturbance, we have, let me say, this, this equation. If I include the disturbance with, for instance, here I did include any other uncertainties. If I include the disturbance, the unique element which can compensate the disturbance is here in order to obtain the Lyapunov function, or the Lyapunov condition, better to say. This is the active element on the surface, of course, on the surface. Let me see if I can justify a little bit better. Yeah, because on the surface, not forget that we have also this, the derivative must be 0. And this means this disturbance which is here must be compensated. To remain on the surfaces. Let me see if I have something better mathematically. Probably, yeah, here. Now we can, let me show you, let me write. This is an important point to be understood. I try to simplify. There is also other possible interpretation. Look at this now with the disturbance. Just the disturbance. Of course, I can add any other uncertainties. It does not change this B, the beta, yeah, SGN or S of t. No? Is exactly this which I copied again. We know that if I already told you now, if we have this condition here, we obtain uh, the negativeness, no? With B larger than this, with B larger than this. But here is exactly this. Now, what is the meaning of this? Remember, this is S dot equals that I will remain on the surface. S equals 0 means I am in the surface, and S dot means I will remain on this. I need to remain on this surface in order um, to guarantee uh, the convergence. And the convergence is guaranteed for beta larger than D. This means if beta larger than, let me say so, max D of t, then we will remain, I will remain. This means exactly as I told you, in general, we say it depends now. You remember, I put you switching or corrective was equal B SGN. Huh? This means, as I told you, you correct it equals minus D of t. Huh? No, with minus, I think. Huh? Yeah, this uh, depends on the sign of U. Let me consider with minus. So we have this. Let me think if I can improve. Otherwise, we can come back with the simulation. Okay, and now I don't have in mind. Okay, I take 5 minutes really to think a little bit, and then I will simulate this easy example, and then we will come back on this concept. Give me 5 minutes, and then we will do the simulation together, and we will come back on this thing a little bit more concretely with Simulink. We go ahead with lecture now, Matra Matra. I am opening MATLAB. Yeah, I'm opening. Then we will see a little bit more in depth. Mhm. I'm looking. Okay. A little bit slow. The problem is now I open in an old version. I hope that I can open the Simulink. Let me see. Yeah, it's a little bit slow. Uh, okay. No, the problem is I open erroneously 2 times or 3 times because the program did not answer. Let me try to close one, what at least one of them. Okay, let me see if I can close this. It's a shame, this MATLAB. Okay. It's really slow. I hope. So I think you should see MATLAB now, but it's extremely slow. Um, Let me close some windows. extremely slow. It's a shame. Okay, now I hope to be able to continue with this. Now let me zoom. Really, zoom isn't a problem. Let me close this. Ah, no problem with zoom, no? I see. I hope that you can see me. Probably with zoom again now. Okay, let me share what I have in MATLAB. I hope that it will work. Okay, look. Let me look at the file if I find. Okay. Let me see where I can find now the file. Okay, here. Um, why can I open this? Ah, MATLAB really. This is impossible to work in Zoom. I don't understand why it doesn't work now. I cannot open. Okay, let me look at another folder. You have a problem with Zoom now. I see that. Let me see. Okay, let me see if I'm able now to open this file. We need time again to open Simulink because I made a mistake because I see that one MATLAB is pending again because I clicked twice. I'm not able to open Simulink. Strange because I opened. No, probably. Yeah, okay. I hope now to show you something. No, this is a different thing. Really doesn't make sense, this MATLAB. 1 second again. Ah, really. To work with Zoom, with MATLAB in this situation does make sense, believe me. Why don't close it? Everything is blocked. Okay, let me try to open again. Probably. Ah, okay. I hope that I can see now. Let me share. Why I don't see? Ah, now I see it. Okay, finally. It's always the problem in where is the file? Excuse me again, but yeah, it doesn't make sense to work in MATLAB with Zoom. They don't open the window. Let me see. It's pending again the Simulink. Let's wait. Okay, I hope now. Finally, I think. Finally, I think you can see the Simulink. Look, here inside, we have our, you remember, x squared minus squared plus 2 times u, the system. Look here inside. Ah, impossible. Look, I put 0 because we don't have, we have the real part of the system equals 0. We have x squared, but x squared, I basically realized here, if you look here, we have 3 possible inputs. Let me look if I can remember. This is the input. I put 2, 1 in order to show you the robustness. Really should be 2. If you remember, I don't want to go out because otherwise you have a problem with Zoom. But if you remember, the control law was excuse me, the system was 2 times u minus x squared, as I told you, as I told you. This means here we have the input, and then of course I can simulate an error in the factor 2. We have minus 1 because we will see from outside I put x squared, and 1 because I put an input as a disturbance. C equal 1, this means the matrix D consists of 1 row and 3 columns, because you remember the matrix D consists of the number of row equals the matrix of D at the number of row equals the number of row of C, and the number of column of D as the number of column of B. I don't know if you remember. I put an initial condition just to start. Mm. How I realize here x squared? So this is x because c equal 1. I multiply by x, and I put on the second input, you remember, because we have a minus 1. Here's the disturbance which I have, one a constant, but I can put whatever kind of disturbance. We will see together. Look now at the simulation. The input u of t is this one, which is multiplied by 2 by the system. But this part here consists of a corrective point part, the switching part, and the equivalent one. What is the equivalent one? Do you remember the equivalent one was 1 divided 2? Let me share. which multiply r plus x squared. Basically, I try to cancel and divide 2, which multiply u1 plus u2. Now we will see what u1 is, should be r of t, and u2 should be x squared, or vice versa. Could be also vice versa. Here we cannot recognize. No? But in any case, we have, excuse me, the equivalent is r derivative. I think it should be u2 in this sense, r derivative, and x squared. The other part is u1 should be squared. Let me see. Let me see. Exactly. No? The equivalent part. Exactly. We can see here. No? U1 in accordance with this function is this here x squared, and U1, U2 is the derivative of the reference linear. I put here in the sinus. The corrective part, we have here in a beta 1000, and here I put the corrective part, which we can see here inside, uh, which consists of approximation. The rest of the correct consists of approximation of the SGN function using, let me share, is an arcotangent, I think. Let me see, I don't remember. Yeah, 2 divided pi multiply arcotangent. The argument is gamma multiply u divided 1 divided 2. Gamma is relatively large in order to approximate well the sign. See, let me show you S of t a little bit better. No? Of course, I don't have SGN because I would like to approximate. Let me show you a little bit better. Ah, excuse me again. To share here is extremely, excuse me, is extremely difficult. Here inside, U, we have inside the matrix, the function, U is S of t. I don't know if you see it. S of t in this case is extremely easy because it's R of t minus the state. We don't have easiest surface than this one. We will see next week that the surface could be also in a complex function of the error, could be also in a differential equation of the error. And a differential equation of the error. Now is the easiest one, just to understand the concept. Let me simulate. And the argument is u, which is the argument of the arcotangent. We have a disturbance and a constant disturbance. Let me see what happens. As I told you now, you see this extremely long simulations because the computer is extremely busy with Zoom, with everything. Okay, let me show you X. Uh, Instead of X, let me show the results. Despite the disturbance, excuse me, it's extremely slow again. Despite the disturbance, despite, yeah, the initial conditions, let me stop. We have this result, which is not bad, no, if you think. Do you remember the initial condition was 100? I showed you quickly, but I showed you. We will see the convergence. And of course, here a little bit too short time, but if you consider a little bit larger, we can see, yeah, numerically is not so nice. We can improve using a better approximation of a function SGN. We can using different simulation tools, different solvers in the sense. But anyway, we can, yeah, of course, yeah, the error is quite big. We can improve reducing also beta, no? A little bit better. Let me show one thing. Next week, we can look on some aspects a little bit better. Robustness, the large, how large is beta and so on. Let me show you here. What I am doing now, I would like to look. It's a shame, it's extremely slow. The corrective part, I would like to see. Why is not possible to see anything? Strange. I don't know if I didn't run, probably. Ah, it's blocked again. Let me see. Ah, it's blocked, yeah. Okay, let me filter. This signal here. 1 second. I would like to show you, look. If I put here disturbance a little bit more consistent, for instance, we will see next week how increasing beta I can correct. At this moment, it seems to be beta 1000 or something like that. Let me show you now if it's working nevertheless. It should work because beta is 1000. Let me see. Okay, also with this system here, should achieve the results, I hope. Yeah, I show you what I intend. And next week we will discuss, let me share. We'll discuss, I hope that we have less problem with the connections. 1 second. I will show you that despite, I hope you see, Anna, despite the disturbance, yeah. Of course, we can see that it's not perfect, but you have to consider, I don't know what we have approximated. I think we approximated, just let me show you with you, the SGN. This means must be considered as an, here we have SGN is not SGN, but is approximated. And then let me see if I put some different things. I think this is the reason of our not perfect tracking mathematically is one thing, practically is different. We will see next week changes beta when we have the stability, when we don't have the stability, and so on. And then we will look together also at the disturbance. At this moment, the disturbance is this signal here. Do you remember at the beginning I put in a constant? Now I put something more complicated. If I put here in a constant, the last test, with an amplitude 1000 could be a problem to obtain the stability, because you remember beta must overcome the uncertainties. The uncertainties now is 1000, you can see from here. Let me see, 1000 is in a marginal case, but should be a problem nevertheless. 1000 comma something should be not possible to obtain the stability. Let me see. I'm running a simulation just to flesh out what I will do next week more in depth, and then I will present in a more complicated case in which the surface S isn't a function of, of the state, isn't a differential equation too. S, we have seen also before at the beginning, because you remember, was x2 equals minus c1 x1. But x2 is the derivative of x1. This means it was already in a more complex, let me say, surface as it's running. But of course, with this value, it seems to be that is running, but it does not find, because of course, with these big values, I can redo the same exercise, put in here 10, and putting instead of this beta, let me say 9. This should generate instability. Yeah, let me see. Because with big values, it could be that you have some problems. Yeah, look. The next week we will go in depth with such kind of analysis. No? We can see the instability. No? We can see the instability. Let me put now, and then we will conclude for today, because it's extremely heavy to do the simulation with these instruments in Zoom. Let me write now, instead of 9, 11. of course, we have the convergence, but of course, the 11 is in a convergence, but probably we need time. No? We need time. Larger and larger beta parameter, in this case, guarantees faster and faster convergence. Why that? Because of this. This is the initial condition. Do you remember? Because the shape of the manifold, the shape of the dynamics, let me say, roughly speaking, is different with respect to different value of beta in our case. No? We have here two possible value. We can recognize intuitively which is the fastest one. Now, should work, let me see, but the convergent will be slow or relatively slow. No, I mean, we can increase the convergence increasing beta. Let me show. If you remember, with 1000 was extremely fast. Yeah, numerically can be improved. Can be improved, of course, numerically. The big problem, I think, is this approximation. Very often we use hyperbolic tangent. We can try also with SGN, but not always it works because AGN is in a particular function that we can see. We can see here. Now, let me conclude here. If you want, I can put another value for eta instead of 11. I don't share. Let me write 110. This means should be faster. Yeah, you can see. No? I said a bit that the shape of the convergency is faster and faster. Let me share. Okay. Yeah. Also numerically, no, we can see a little bit better. This is difficult. Yeah, we have a bias, but this can be improved if you let me see if you approximate the SGN a little bit better. Let me try it. Yeah, let me see. Small, we don't have better, but we will see next week. Probably we can try directly with SGN. Or it could be that we have to change the solver because, yeah, this depends also on the solver. Okay, let me conclude here. Let me come back to you. Today, we will reanalyze this next week. But very important that we will see another more realistic example in which also the surface plays an important role in the sliding. This surface is the it's a static surface. We will see some way how we can approximate also better also the solution. We will see that we have this bias, it should be somehow reduced or eliminated somehow. Okay, nevertheless, we sketch the basic knowledge. Next week, we will go ahead with some more realistic example. If you have question, we can discuss now. Otherwise, okay, next week, more or less at the same time. Thank you for your attention.
Thank you. Goodbye. See you next week.